Hello, it's me, Chris. Many years ago, I made a series of videos called Character Stats. In those videos, we implemented a system that manages stats and their modifiers and bonuses, as usually seen in RPG games. You can use that system to implement stats or attributes, if you will, in your RPG characters or any other entity in your game that needs similar functionality. This can range from a character increasing their strength or their agility to a machine gun in an FPS increasing its rate of fire. Even though the concepts in those videos are just as relevant today as they were then, in my humble opinion, in the meantime, I've learned a lot about programming, and specifically programming in Unity and C#, and today I would like to revisit those systems and make some small but very significant improvements. Our stat system consists very simply of two classes, one called character stat and the other called StatModifier. The character stat stores a list of stat modifiers that can be of different types, and when needed, it calculates the final value of the stat based on all of the different modifiers. And the stat modifier stores information about the type and the amount of modification that we want to apply to the stat. If you haven't watched the original videos, I would recommend you do so. There will be a link appearing for the playlist in the top right corner of the screen. The videos are quite short, around 10 minutes per video, so if you want to pause this one and go take a look at those, I'll see you back here in a bit. Now for the improvements that I would like to make here, let's start out by taking a look at the performance characteristics of the original code. For that, we will open the profiler window. The shortcut to do that is Ctrl+7. We will also activate the deep profiling option, so we have more details. For the performance tests that we'll be running, I've already made a script for it. And what we're going to do is, we'll be generating a set of 100 stat modifiers at random every frame, and then we will add 10 modifiers and remove them, 100 modifiers and remove them, and then we will add again, instead of removing the modifiers directly, we'll remove them by using the source variable. And the reason we have functions to add and remove these different amounts is so that we can see the performance scaling of adding just a few modifiers or adding more. And we also repeat everything 10 times each frame, just to make sure that everything is very much visible on the profiler, and so that we also simulate essentially adding and removing modifiers from, let's say, 10 different entities in your game. So we have our performance script attached to a game object in our scene. So if we press play now, we can see that one of the main issues of this system is the amount of allocations that it generates per frame. So all of these allocations are objects that we have instantiated that will need to be garbage collected later. And as you may or may not know, garbage collection in Unity can be a big source of stutters in your game. We want to try and avoid generating garbage as much as it's reasonable, so that we avoid those garbage collection spikes. So one of the biggest sources of allocations that are being generated is simply by generating the modifiers themselves. And why is that? It's because StatModifier is a class, so every time we write new StatModifier, we are generating a new allocation. However, for a class such as this, where all of its values are read-only, and most of them are value types as well, it really doesn't need to be a class at all. So the first change that I want to do is change this into a struct instead of a class, and VS Code will also suggest that we can change the struct to be a read-only struct, since all of its members are already read-only. And I'm also going to add the nullable reference notation here, just because I'm using this in my project. You don't have to do this if you're not using it. So we can go back to the profiler, run it again, and we can see that generating the modifiers now allocates 0 bytes. However, you may have noticed that everything else started allocating much more and also became much slower. Why is that? So when it comes to the remove function in particular, in order to remove an element from the list, we need to find it first, right? And in order to find it, an equality comparison is done until we find one that matches the object we want to remove. And for structs, the default behavior in C# for equality comparison is that an automatic equality comparison will be generated for us, and unfortunately, that default comparison tends to be quite inefficient, and in this particular case, it also generates a lot of allocations. Luckily, the fix for that is very easy. All we need to do is implement the IEquatable interface in our StatModifier struct, and the IEquatable needs a generic parameter, and this will be of StatModifier as well. So basically this is saying that we want to make our StatModifier have an equals comparison to other StatModifiers. So we can ask the editor to implement the interface for us, and the equals function will very simply be comparing each value of our object with the object that has been supplied as an argument. So we compare value to the other value, type, order, and source. Since we have implemented the equals method from the IEquatable interface, while we're at it, we can also implement the equals override. And while implementing the equals override, it's also good practice to implement getHashCode. So for the equals override that receives object as parameter, we will check if the object is also of type StatModifier. If it is, we cast it to an object of that type, and we use it to call the equals method that we just implemented. For the hashcode, we can make use of a new-ish C# struct that's simply called hashcode. So you do hashcode.combine, and then you pass in the different values that you want to use for the hashcode calculation. In our case, we will pass in everything: the value, the type, order, and the source. One other small optimization that we could make here, even though it's not especially relevant in our particular use case, we may as well do it anyway, and it's a good thing to keep in mind for other similar use cases that you may have. So for an object like this, that is read-only, we know that the hashcode is not going to change because none of the properties in the object are going to change. Or at least it shouldn't. The hashcode definitely shouldn't change for a read-only object. So what we can do, actually, is store the hashcode calculation in a variable, and then we calculate it once at object construction, and when the getHashcode function is called, we just return the value that we saved instead of recalculating everything. So let's go back into Unity and test things again, and as you can see, the performance characteristics of the new code, where stat modifiers are structs, are now equivalent to when they were classes, with the added benefit that we are not generating a single byte when generating the modifiers. You may notice that it's actually slightly slower than before, and the reason for that is that we are calculating the hashcode at construction time. So if you don't have any use cases where the hashcode function is relevant for the stat modifiers, feel free to just delete that part. So yeah, if we do that, we can see that the performance is actually slightly better than before, with 0 allocations as well. However, we still have tons of allocations in all of the other functions. Let's figure out what's causing them. So this is coming from the getValue. In the calculateFinalValue function, something is being allocated. So let's take a look at the code for that and see if we can figure out what is happening. For the untrained eye, looking at this, nothing really stands out that could be causing allocations, right? However, if you're a bit more aware of how certain things in C# work, there's one thing that immediately stands out, and that's this line over here. So when you pass a function into another function, C# has to generate a delegate. It basically means it needs to store this function in a variable. And the process of doing that incurs in allocations. So what we can do to avoid this is, instead of passing in the function directly here, we store it in a delegate ourselves, and then we pass that delegate. So the allocations only happen once, and then we reuse the object that was allocated. So let's do that. We can first check what this sort function is receiving. So it's receiving a comparison t, and if we navigate into that, we can see that it is a delegate type. So in our character stat class, we just declare a comparison variable. So it's a comparison of StatModifier. And in the constructor, we store our compare modifier order function. And now here, we use the delegate that we stored rather than the function. Let's check the profiler again. And as you can see now, we have 0 allocations in almost all of the functions. Now for the last bit of memory allocations that we are seeing here, this is happening in the remove all modifiers from source function. So let's take a look at that. If you pay attention, a very similar thing that was happening here in the sort function below is happening up here as well, which is the remove all function from the list receives a predicate. This predicate is a delegate, which means that this argument here that we're passing is allocating every call. Unfortunately, in this particular case, as far as I'm aware, there is no way to eliminate the allocations that we are seeing. And the reason for that is that this delegate here actually depends on the parameter that is passed into the function. That means that every call, a new delegate is being generated, which captures this outside variable. So in contrast to the compare modifier order function, the same function with the same arguments and the same code is being used for every sort call. Up here, however, it's essentially different functions that depend on a different source object every call. So as far as I'm aware, there is no way to eliminate the allocations here. If you do know of a way, please let me know in the comments. So if we compare our updated code here with the old code, so here on the right I just reverted all of the changes that we did just to compare the performance of the original code. And as we can see, not only did we eliminate the vast majority of allocations, we also improved the performance slightly. So I'd say these are pretty big wins for very easy changes that we just did. Now, I think we can do even better, and in the next video, I'll be showing you a new stat system written completely from scratch, where the performance is generally much better than the old system. The code for the new system is a little bit more complex, to be fair, but it performs better, especially as you start adding large amounts of stats into the system. So, thank you for watching, and I will catch you again in the next one. Peace.